The 555 chip is more or less the ideal square wave generator. That can be used in many ways, but anyway, when you don't want to use such a 555 chip, there are many videos about that on YouTube, by the way. But when you don't want to use that, this is an old schematic from the 1970s. I found it in a British magazine, ETY, I think. This, you can find it on the website of worldradiohistory.com. Go to the British flag and look to the magazines there. I adapted this schematic somewhat because I found some problems, but anyway, let's go first to the schematic itself. Here it is. It is a classical multivibrator circuit where we see the collector directly connected to the base, the second transistor to the first transistor, and from the first transistor to the base of the second transistor. That is not always made in this way, and it means that it has good properties, at least in this case. There is here a timer capacitor that is CX, and I will demonstrate more about it. Here are, say, the values that generate a certain frequency. 18 microfarad, we are on 81 Hertz, 1500 picofarad on 560 kilohertz, and 500 picofarad we are on 1.8 megacycles. But the important thing is that frequencies higher than approximately 800 kilocycles or 1 megacycles turn a little bit into sine waves. I will demonstrate it. So this is, say, the frequency range. The waveforms get, say, somewhat rounded on these higher frequencies, etc., etc. The magazine told that this was a constant current source. I'm more or less sure that it is completely correct. I did some adaptations, bridged this resistor with 27K, bridged this resistor with 100 ohms, and found a way to take out the square wave opposite to the minus. In the original schematic, I could not find a ground or a minus. That is in a certain way very okay, but it makes the circuit less usable for practical purposes. When, for instance, there is no this connection is not made, it means that you can here derive from parallel to that capacitor a very, very pure triangle wave, and parallel to this 330 ohm resistor a very pure square wave. But they say are in a certain way not related to Earth or so. So you have to find a solution for that. I could not find a solution for that, and that's the reason why we see the circuit as it is. Where the minus is now here, oops, connected to ground. The emitter is now connected via 1 microfarad cap non-polar and a 1K resistor to ground, so that we can take out here frequencies, square wave frequencies. The voltage is very critical. Best results are on 8.4 volts, perhaps on 9 volts. You can test and try. One of the aims of my YouTube channel. So let's look to the scope. Where will the oscillator work, and I've used 3 capacitors, and here is the waveform. It's now on 80 Hertz, but you can get to 50 Hertz and 60 Hertz by turning this potentiometer here or this potentiometer here, 2K2. This is a switch that has in fact no real purpose, but anyway it's the same as where we connect the 2K2 resistor directly here to the positive lead. So when you are a little bit acquainted with electronics, you will surely know that. So here's the waveform. It is 15 November 2025, 82 Hertz, and I will now try to turn the important potentiometers. Now I turn that 500 ohm potentiometer in the schematic. Let's see what happens. We are on 80 Hertz. This happens. Now we are on 53 Hertz, 60 Hertz. So it has an effect, and it has of course to do with, say, the current that is sent into this circuit. So anyway, that's one idea. I switch now from the lowest frequency to the highest frequency. That I do that by purpose. You can use a rotary switch, of course, when you want to use this circuit in a practical way. Switch now directly to the highest frequency that it can give. It stops. That's very strange. Oh well, I hope. Well, I have to do some soldering work. Sorry for that. Was not my idea, but the soldering iron is on. So now we switch to the highest frequency. Yes, here it is. And it is. But you can directly see that the waveform is no longer a pure square wave. It looks a little bit like a sine wave here. And we are on 1.7 megahertz. Well, that's quite high for such a simple circuit. Looks a little bit still like a square wave, but anyway, perhaps when you use real high frequency transistors, could be that it works better. I didn't test that. I'm going to do more other experiments. And now I turn that 2K2 potentiometer in the collector lead of the first transistor of the multivibrator. Let's see what happens. So, well, changes from 1.1 megahertz to 2.2 megahertz. But again, waveform changed more or less into a sine wave like waveform. Could be that you do not use that, do not want to use that. Anyway, this was more or less all to tell. Thanks for watching, by the way. Let's do a final experiment and turn that 500 ohm resistor that is responsible for the current. I've forgotten to tell that the magazine told that this is a constant current circuit. At least the first two transistors that drive the multivibrator. So here again, turn that, and we are now 1.7 megahertz. I think that's not very interesting when you want to do serious experiments. This is 2.2 megahertz. Could be a very interesting schematic for a certain purpose. for one frequency, or to make a generator in cases where you don't want to use that all overused 555 chip. That works, by the way, up to 500 kilohertz. So this schematic goes higher, though not a flaw, but say the property of the circuit is that on frequencies higher than 1 megahertz, the waveform is no longer a sharp square wave. Thanks for watching again. And let's look at the beautiful waveforms. By the way, here is the schematic on the breadboard. Brass nails, well varnished wood. So, that was all.